So the absolute value of x is equal to x if x is positive, but it's equal to negative x if x is negative. So what's going to happen here is we're going to say that the square root of 2 cosine squared of 3x is going to equal, well, you're going to have two different options, right? You're going to have the square root of 2 times cosine of 3x if cosine of 3x is positive. And it's going to equal the negative square root of 2 times the cosine of 3x if cosine of 3x is negative. Hopefully everyone's okay with that. I can talk more about why that's true, but we're just saying, right, if your stuff is already positive, then leave it alone. If your stuff is negative, make it positive by multiplying by negative 1. Oh, I should turn on my AC in here. It's a little bit too warm here. Oh, there we go. Okay, so when is cosine of 3x positive? Well, it's positive when we're in quadrants 1 and 4. So basically, this is positive if our angle 3x is between 0 and pi over 2. Which, if I divide everything by 3, it means x is between 0 and pi over 6. Cosine of 3x is negative in quadrants 2 and 3. Quadrant 2 specifically is when our angle is between pi over 2 and pi. And so if I divide this by 3, it's when x is between pi over 6 and pi over 3. So the thing here is I can't actually just say, never enough room. So I can't just say, I guess I'll erase it here for a second. I can't just say that this is equal to the integral from 0 to pi over 3 of the square root of 2 times cosine of 3x. Yes. If you did this, you would actually get 0. But it shouldn't be 0 because this function, a square root always gives you a positive result. So if you're integrating something that's always positive, it shouldn't equal 0, right? You're integrating a function that's always above the x-axis. You have some positive amount of area, and there's nothing below it to cancel that out. So this equaling 0, which it does equal, right? If you integrate this, you get square root of 2 sine of 3x divided by 3 from 0 to pi over 3. If you plug in pi over 3, sine of pi is 0. If you plug in 0, sine of 0 is 0. So this would equal 0. But it shouldn't be 0. And the problem is exactly this issue here, that you have to break it up. So what you actually have to do is, I'm gonna write this over here. So this is when x is between pi over 6 and pi over 3. And this is when x is between 0 and pi over 6. So I can use this space here. We actually have to break this integral up into two pieces. The integral from 0 to pi over 6 of the square root of 2 times cosine of 3x plus the integral from pi over 6 to pi over 3 of the negative square root of 2 of cosine of 3x dx. Fun times. So then, let's fine. We'll go to the other side. No, we'll go up here. Fine, we'll go up here. I feel bad erasing parts of the problem halfway through. But so integrating cosine of 3x, we still get sine of 3x divided by 3. So you get the square root of 2 times sine of 3x divided by 3 from 0 to pi over 6 plus the square, minus, right, because really no minus there, minus the square root of 2 times sine of 3x divided by 3 from pi over 6 to pi over 3. Okay, so plugging in pi over 6, you get the square root of 2 times sine of 3 times pi over 6. I'm not quite sure, Daniel, as far as like I don't always have a real specific plan, but yeah, I'm probably gonna start talking about things that are gonna come up next week. So I'll definitely get the video posted at some point later today or maybe early tomorrow, so you can watch it. But yeah, we might talk about things for next week, depending on what you guys want. Right? If you ask for things, I will do them. So plugging in pi over 6 here, 3 times pi over 6 is pi over 2, and sine of pi over 2 is 1. So I'm gonna get 1 over 3 minus the square root of 2 times sine of 0 is 0. Minus, now we plug it over here. Plugging in pi over 3, 3 times pi over 3 is pi, and sine of pi is 0. Minus plugging in pi over 6. In fact, we know we plug in pi over 6. Sine of 3 times pi over 6 is the same as over here. It's going to give you 1, right? Sine of pi over 2 is 1. So we're going to get root 2 times 1/3. So we end up getting root 2 times divided by 3 plus another root 2 divided by 3. So you get root 2 over 3 plus root 2 over 3, which is 2 root 2 over 3. So that's how you do a problem like that. So just to point out, in the problem I'm seeing on the homework assignment, which is a little bit different looking, but I'll show you how.
I have a question on this problem.
Okay, go ahead.
So you did it this way only when it gives you 0? Like if you try to solve it directly from 0 to pi over 3?
So I did it. So you mean the breaking up part?
Yeah, the breaking up part.
So it's more that I had to think about when my function is positive, when my function is negative. And so what I'm really doing is I'm thinking about the quadrants, right? I know that the cosine function, right, is positive in quadrants 1 and quadrant 4, which is when my angle is from 0 to pi over 2. And then, right, quadrant 2 is pi over 2 to pi, and then 3 pi over 2, and then 2 pi. But I know that my limits of integrate. Well, so the problem is there's kind of a lot going on here, right? Because my angle is really 3x. So I'm starting with the fact that my angle 3x is between 0 and pi over 3, which feels kind of wrong. It does feel kind of wrong. One moment. No, sorry, that's a little bit wrong actually. Apologies. What I should really be saying is x is between 0 and pi over 3. Right? These are x limits of integration. But my angle is 3x. So I really have 3 times 0 is less than 3 times x is less than 3 times pi over 3. So that my angle is between 0 and pi over 2. So then knowing that my angle is between 0 and pi over 2, why does this feel like it's working out very differently when I do it this way? Sorry, something weird is happening and I'm not quite seeing it. Yeah, apologies here. One moment. Oh, sorry, I'm making a dumb algebra mistake. 3 times pi over 3 is pi, not pi over 2. Okay, so what we're seeing here is that our angle 3x is between 0 and pi, which is the first quadrant and the second quadrant. So in the first quadrant, which is from 0 to pi over 2, we have to have everything is already positive. But in the second quadrant from pi over 2 to pi, the cosine function is negative. So we have to make it positive by taking the negative of it. So that's kind of what's happening there. We're essentially, so, and that's not really the way I did it because I kind of already knew it was going to happen. Let's look at another example of this just to kind of solidify things.
James, just a quick remark on this problem. So you said why would we have to check the second quadrant once again?
Why?
Yeah, like why? I just thought we would just have to check from 0 to pi.
Well, pi, so pi,
Oh yeah, pi is a
pi is the second one.
yeah, true. That's
Okay.
very
So let's look at another example. This is straight from the homework, or at least from my homework. The integral from 0 to 7 pi of the square root of 1 minus cosine of 2 pi over 7. 2x over 7, not 2 pi over 7, sorry. Over 2. If you really wanted to make this easier, you could do a u sub for 2x over 7. I don't think that's really necessary, but it might make seeing the angle sub a tiny bit easier. I'm not going to do that, but I can if you guys want me to. That sort of thing. It's hard to see. So again, right off the bat, I see a trig identity here. I know that sine of an angle is equal to 1. Well, this one's going to be easier. It's okay. It's going to equal 1 minus cosine of 2 times that angle divided by 2. Sorry, sine squared of an angle is equal to 1 minus cosine of 2 times the angle divided by 2. So I'm going to replace my angle theta with x over 7. So that my 2 theta is 2x over 7. So sine squared of x over 7 is equal to 1 minus cosine of 2 times x over 7, all over 2. So great. I can replace what's inside the square root here with sine squared of x over 7. So I'm going to get the integral from 0 to 7 pi of the square root of sine squared of x over 7. Okay, now I'm going to think about the fact that x is between 0 and 7 pi. But then I'm actually caring about the fact that my angle, the thing I'm taking the sine of, is x divided by 7. So I'm going to divide everything by 7. So what I have is that my angle, x over 7, is between 0 and pi. Now, in this problem, it's actually not an issue because sine is positive in the first and the second quadrant. So here, it would be totally legitimate to just say that this is equal to the integral from 0 to 7 pi of sine of x over 7. Because sine is positive in both the first and the second quadrants. Let me change the problem a little bit. Let's say instead of going to 7 pi, we were going to 21 pi over 2. So 21 pi over 2 divided by 7, well, 21 divided by 7 is 3. So you get 3 pi over 2. And now we have issues because our angle is going from 0 to 3 pi over 2. And I think I'm going to erase this here. What that means for us is that right, we're going from 0 to pi over 2 to pi to 3 pi over 2. Here and here, sine is positive. But down here, sine is negative. So we have to break this up. We have to break it up where 0 goes, x over 7 is between 0 and pi. That's going to be my first breakup. And then my other one's going to be x over 7 is between pi and 3 pi over 2. And then multiply it back by 7 so that x is between 0 and 7 pi. And then here, x is between 7 pi and multiply by 7, you get 21 pi over 2. So the way you would do this integral, if you give yourself funkier limits of integration, is this would have to end up being the integral from 0 to 7 pi of just sine of x over 7 plus the integral from 7 pi to 21 pi over 2 of negative sine of x over 7. And again, the reasoning behind this is because from 0 to 7 pi, sine of x over 7 is positive. But from 7 pi to 21 pi over 2, sine of x over 7 is negative, but we need it to be positive, so we throw on a negative sign there.
James, I have a quick question. So pretty much did it just added an extra part to the problem?
So the actual problem you guys have, you don't probably have to worry about it being negative anywhere, because it ends up being equal to sine squared. And on the limits of integration, you have your angle is between 0, or at least my angle is between 0 and pi, meaning that we're in the first and second quadrant where sine is always positive.
Okay, for sure. Thank you, James.
Okay, let's look at the problem actually that's right before that as well, because it is also kind of super funky. Now there's actually two ways of doing it, which I think we should talk about. So here's the problem I've got. It's the integral of sine of 4x times cosine of 3x. And I honestly, so to be perfectly honest, I never had to do problems like this when I was in Trinity. This is one section my teacher might have skipped or something. There's a couple different ways of doing this problem. So if I want to do the integral of sine of 4x times cosine of 3x dx. One way of tackling it is to use a trig identity. So there's a trig identity, it's the angle sum identity for sine. Sine of a plus b is sine a cosine b plus sine b cosine, or plus cosine a, doesn't really matter, sine b, and then sine of a minus b is equal to sine a cosine b minus cosine a sine b. And so if you add these together, you get sine of a plus b plus sine of a minus b. These parts cancel, and you get 2 sine a cosine b. So what we're going to do is we're going to say then that sine of a times cosine of b is equal to 1/2 of sine of a plus b plus sine of a minus b. Okay, great. So in this problem, that's our a and that's our b. So the integral of sine of a times cosine of b, well, sine of a times cosine of b is equal to this. So it's going to be 1/2 the integral of sine of a plus b. So right, again, that's my a, that's my b. So a plus b is going to be 4x plus 3x, which is 7x. And then plus sine of a minus b. So a minus b is 4x minus 3x, which is just sine of x. I never really knew this trig identity when I was in calculus, but you can use it, and then you get 1/2. So let's see, the integral of sine of 7x is negative cosine of 7x divided by 7, and then the integral of sine is negative cosine. So our final answer would be negative cosine of 7x over 14 minus cosine of x over 2. Interesting. Let me show you a different way that might seem more natural to you. Again,
A quick question on this problem.
sure.
So, how would it It doesn't matter that we have sine and cosine for a problem, but in the identity it just says sine A plus B.
Right. So specifically, this is the identity to use when you have sine of an angle times cosine of a different angle.
Oh, okay.
So in fact, it does matter, and we are very specific here. And we're saying, so basically, I'm using these trig identities. That sine of A plus B is sine A cosine B plus cosine A sine B, and sine of A minus B is sine A cosine B minus cosine A sine B. And then adding these together to cancel this part out, so that I get something that looks like sine of one angle times cosine of a different angle.
Oh, all right. Okay.
And I'm dividing the two out. So then I'm saying, oh, sine of 3x times cosine of, sine of 4x times cosine of 3x is going to be sine of 4x plus 3x plus sine of 4x minus 3x.
That makes sense, James.
It's a little weird. I'm not going to lie. So there's another way you can do this, which is, so I will say this is the easier way, but maybe the less intuitive way, right? Like I don't remember this ever. I'm like, oh yeah, there's this formula for sine of an angle times cosine of another angle. It's always super funky. The other way is maybe slightly more intuitive in that it's probably easier to think of on your own, but the actual calculation or computation is quite a bit uglier, I would say. So you can also do this using integration by parts. So an integral of sine of 4x times cosine of 3x. This is going to be one of those terrible ones where you have to do it twice and then you get back what you started with. So we're going to let u equal sine of 4x. dv is going to be cosine of 3x dx. du is going to be cosine of 4x times 4 dx. V is going to be the antiderivative of the sine of 3x divided by 3. It doesn't actually matter which one you pick for u and dv, but it just matters that when you do it the second time around, you make the same sort of choice. We have to be kind of extra careful here. So we're going to end up getting u times v. So it's going to be 1/3 sine of 4x times sine of 3x. Minus the integral of v du, which is going to be, so I got a 4 times a third, so I got a 4/3, and then v du is cosine of 4x times sine of 3x. All right, so now what we're going to do is we're going to do integration by parts again. And we're going to make this, when I say we're going to make the same choice, we're going to make the choice where u is essentially has the same kind of inside part for the trig function. So here we're going to let u equal cosine of 4x. I'll just point out, if you let dv be what the thing that was du last time, like if I said dv was cosine of 4x, I'd essentially be undoing the work I did. So you never want to let dv be the part that ended up being your du from the previous one. So I'm going to let u equal cosine of 4x. dv is going to be sine of 3x dx. du is going to be negative sine of 4x times 4 times dx. And v is going to be negative cosine of 3x all over 3. Okay. So we're going to end up getting 1/3 sine of 4x times sine of 3x minus 4/3 times uv, which is going to be minus 1/3 cosine of 4x times cosine of 3x minus the integral of v du, which is again a 4/3. And then I've got a negative sine of 4x and the negative cosine of 3x, which is just going to be sine of 4x times cosine of 3x. And the negatives cancel out. All right, so here's what we've got. I'm going to do this thing. So I'm going to call this integral. I am going to call it capital I. So capital I, the integral I just did, is equal to this 1/3 sine of 4x times sine of 3x. And distribute the negative 4/3. Negative 4/3 times negative 1/3 is positive 4/9. And then I've got cosine of 4x times cosine of 3x. And then negative 4/3 times negative 4/3 is positive 16/9. And then I've got the integral of sine of 4x times cosine of 3x, which is what I'm calling I. I'm going to subtract that over. So 1I minus 16/9 I, or maybe 9/9 I minus 16/9 I is negative 7/9 I. So negative 7/9 times my integral is equal to 1/3 sine of 4x times sine of 3x plus 4/9 times cosine of 4x times cosine of 3x. And multiply both sides by negative 9/7. Sure. I mean, I am getting that my integral is equal to, so negative 9/7 times 1/3 is going to be negative 3/7. So negative 3/7 times sine of 4x times sine of 3x. And then negative 7/9 times 4/9, sorry, negative 9/7 times 4/9 is going to be, the 9s will cancel and you'll get negative 4/7. Cosine of 4x, cosine of 3x plus c. So then you have to ask yourself, does this look the same? And the answer is not really, right? That does not look the same as that at all. It is the same, you just have to do work to show it's the same. So the way you would show that these are the same, which is kind of a pain, is you would use the trig identity for cosine. So you would write this as you would write this as negative 1/14 times cosine of 4x plus 3x minus 1/2 cosine of 4x minus 3x. And then there's trig identities for that, which would get you back to this. It's a giant pain in the butt. As far as doing a problem like this, I definitely think it's easier to do it this way, right? The computations are much more straightforward this way. Doing it this way is kind of terrible. So if I had a choice, I would pick to do it this first way. But doing it this first way means you have to use this sort of trig and okay. I mean, and this formula is in your textbook. Like if you look, let me see where in the textbook it is. I think it's in the back. You look in the back of your textbook. I think there's some trig. Yeah, there are some trig identities. Yeah, that's right. So there's a trig identity for sine of A times cosine of B, which is exactly what we have, and it's exactly that. It's exactly 1/2 sine of A plus B plus 1/2 sine of A minus B. Right over somewhere over here. So I know that's really kind of grainy. So you guys can kind of see it right there. So it's definitely in the back of your book if you're looking for it. Fun times. So those are some of the kind of weirder trig integrals that we might have to encounter. On the other hand, there's much more normal things, like what we were talking about last class. For example, I could ask, what's the integral of say secant of 3x plus tangent of 3x quantity squared. This is actually not too terrible at all. That's the integral of, well, if you multiply it out, it's secant squared of 3x plus 2 secant of 3x tangent of 3x plus tangent squared of 3x. All right, so we know the integral of secant squared, it's tangent. We know the integral of secant tangent, it's secant. And tangent squared, we know a trig identity for that. Tangent squared is equal to secant squared of your angle minus 1. So in fact, what we get here is the integral of secant squared of 3x, which is tangent of 3x divided by 3, plus 2 times the integral of secant of 3x tangent of 3x, which is secant of 3x divided by 3. And then the integral of secant squared of 3x again is tangent of 3x divided by 3. So I guess I can just write this as 2 tangent of 3x divided by 3. And then the integral of minus 1, which is minus x. That's it. Yeah.
James, how did you get 2 at the beginning of the tan 3x over 3?
So I was lazy and I said, I know that when I integrate tangent squared, it's going to be really integrating secant squared minus 1. And the integral of secant squared of 3x, well, the integral of secant squared of 3x is tangent of 3x over 3. So I'm getting another tangent of 3x over 3. But then I decided that tangent of 3x over 3 plus tangent of 3x over 3 is 2 tangent of 3x over 3.
Oh, for sure. Yeah, for sure. Thank you.
Oh, yeah.
Wait, James.
Yeah.
A quick question. Could you, what was the, oh yeah, it was just secant squared 3x minus 1.
What was the question?
Oh no, I just wanted to see like the antiderivative for tangent squared.
So again, that's not the antiderivative for tangent squared. That's just what tangent squared is equal to.
Yeah. The identity. Yeah.
Right. This is the antiderivative for tangent squared.
Mm-hmm. Yes.
Of 3x.
Okay. Thank you, James.
You're welcome. Let's see, that's pretty much that. Okay. That's that. That's that. Sure. All right, let me give you guys a problem. Let me actually ask you guys a question. So if I want to do the integral of tangent cubed x times secant to the 5th x, what should we be choosing for u? You can write it in the chat. You can either pick u equal to tangent, or you can pick u equal to secant. And there's definitely a right choice here, and there's definitely a not right choice. It's okay to make the wrong choice. I really want to know, what do you guys think? Should it be tangent or secant? I'm not even sure. I haven't checked this problem. But I know what I want to happen. I want whatever I pick for my u, I want the thing that's not u. After I deal with the du, I want the not u's to have an even number left over. So if I let u equal tangent, my du is going to be, well, first of all, if I let u equal tangent, my not u is secant. Right? So if u is tangent, then not u is secant. I know that seems kind of dumb to say, right? Because obviously the other thing is the not u thing. So then my du, my derivative tangent, is secant squared x. So let me ask you, after I take care of secant squared, how many not u's are left over? Oh. How many are left over?
Would it just be 3?
Right. And we don't want an odd number left over of our not u's. We want an even number left over of our not.
Oh, so on these kind of problems, we have to like pretty much have something evened out, nothing that's
But
already.
you have to think even after you dealt with du, right?
Mhm.
So you have to say, I'm going to pull out secant squared, and then after I factor out secant squared, I'm still left with the secant cubed. And since secant is not what u is, I have to use a trig identity for it. But I can only use a trig identity for an even power of a trig function. Odd powers just don't work.
Mhm.
So let's look at the choice of secant. We pick u equal to secant, then our not u is tangent. So we know that when we're trying to make this work, after we deal with du, we want an even number of our tangents left over. So what's du? What's the derivative of secant?
Would be 16x tangent x.
Right. So I can see that when I deal with my du part, I'm going to take out one tangent and one secant. How many tangents are going to be left over?
Yeah.
An even number, which is good. Our not u will have an even number left over. It doesn't matter that our u will also have an even number. It doesn't. We could care less about u being even or odd. So what's going to happen is we're going to rewrite this. I personally like to write it out so that I have what I want. Meaning, I'm going to write it as the integral of tangent squared x times secant to the fourth x times my secant x tangent x dx. So I can really see, oh yeah, there's my du. There's my u to the fourth. And tangent squared, well, I know that 1 plus tangent squared x equals secant squared x. So tangent squared x equals secant squared x minus 1. But secant is our choice for u. So tangent squared x equals u squared minus 1. So this is going to be u squared minus 1. So then we can rewrite the whole integral as the integral of u squared minus 1 times u to the fourth times secant of, sorry, times not secant of anything times du. And then we have to distribute. So the integral of u to the sixth minus u to the fourth. We have to differentiate. We get u to the seventh over 7 minus u to the fifth over 5. Let's see. And then plugging back in what u is, we get, sorry, brain works here. Plugging back in what u is, we get secant to the seventh of x over 7 minus secant to the fifth x of 5. Let's see.
Okay.
Let me show you another funky one. That one was not too funky. So for sines and cosines, when you have an odd and even power, or when both odd powers, you want to pick u to be the trig function to the higher power, when sine and cosine. When you have an odd and even power, you want to pick u to be the one that's to the even power. So what if I wanted to integrate, let's say I want to integrate cosine to the fifth of x. This is a u substitution and it's super funky. Does anybody know what I should choose for u?
Wouldn't it be cosine x?
It's actually not cosine x. That's what's funky about it. You're like, James, there's nothing else to choose. And you're like, well, there kind of is.
Would you just speak the whole thing and
Or would it be your dx?
What's the derivative sign?
cosine?
So what I want to point out here is you still are meeting the criteria that we usually think of for a sine times a cosine. Right, exactly. Eric is like, oh, I see what's going to happen. So we have cosine to an odd power. We also have sine to an even power. What power of sine do we have here? How much sine is there?
None.
Right? 0 is an even number. We have an even power of sine. When you have an odd power of cosine and an even, or you have an odd, when you have sine and cosine, you have an odd power of one and an even power of the other, you let u be the one that's to the even power, even if that power is 0. Check it out. So we break this apart. We're going to write this as cosine to the 4th x times cosine x dx. There's my du. And my not u choice, there's an even number left over. And we know how to use a trig identity to deal with that. So really what the trick here is that there totally is a sign in this function. I just haven't written it that way, right? We know that cosine squared x is equal to 1 minus sine squared x. So cosine to the 4th x is cosine squared, which is 1 minus sine squared, quantity squared. So really, if you wanted to, before doing the u substitution, you could say, well, James, I know you're just messing with me. I know that we really have the integral of 1 minus sine squared x quantity squared times cosine of x dx. And then it seems a little bit more natural to be like, oh yeah, I can let u equal sine, and then du is going to be cosine x dx.
Yeah, that was my idea.
It's a tricky problem. Like the first time you see this, you're like, what? I'm letting u equal something that's not even in the integral. Well, it's there, it's just hiding. And then this is going to be a u squared. So we get the integral of 1 minus u squared d. And then we multiply it out, we get 1 minus 2u squared plus u to the 4th. And then we integrate, we get u minus 2u cubed over 3 plus u to the 5th over 5. And then we write it up plus c. And then u is sine, so we get sine of x minus 2 sine cubed of x over 3 plus sine to the 5th x over 5 plus c. Okay. Let me show you another similarly tricky problem. So in this previous one,
James,
yeah.
do you flip over the whiteboard real quick?
Sure. Good? I'm sorry.
Yeah, thank you, James.
Oh, so similarly, we could try to integrate something like secant to the 6th. So, any guesses what we might let u equal?
Tangent squared or something.
Simpler, but you're on the right track.
Simpler.
Just tangent.
Not almost.
So typically when you do a u sub in general, you're almost never, well, I should back that up. When you're doing specifically with trig functions, you almost never want to let u be like a power of a trig function. You want it to just be the trig function.
Yeah, I realized that too. When you're doing these kind of problems, that's pretty much where you're going to take the integral of after. You don't really leave it untouched until you take the integral.
So then my du is going to be secant squared x dx. And great, my leftovers of my non-u things, which is secant, there's going to be an even number. This is going to be the integral of secant to the 4th x times secant squared x dx. And then I'm going to remember that secant squared is equal to 1 plus tangent squared, right? I tan and gets x, everyone's favorite trig identity. So then, oh yeah, secant to the fourth x is just going to equal 1 plus tangent squared x quantity squared, which is just going to be 1 plus u squared squared. This is going to equal the integral of 1 plus u squared squared, right? That's what that is right there. And then that's going to be my du. Very similar to the previous problem. So then we get the integral of 1 plus 2u squared plus u to the fourth du, which is equal to u plus 2u cubed over 3 plus u to the fifth over 5 plus c. And then we get tangent of x plus 2 tangent cubed x over 3 plus tangent to the fifth x over 5. All right. Exciting. So again, with these powers of trig functions problems, you're always trying to make the choice for u so that your not u thing, after you've dealt with du, there's an even number of your not u's left over. That's always what we're looking for. And you can almost always make it work. There's two situations where it does not work. So the only times it doesn't work is if you have sine and cosine both to an even power. So if you have like the integral of sine squared x times cosine squared x, no u sub here. You have to do the trig identity where sine squared x equals 1 minus cosine of 2x over 2, and cosine squared x equals 1 plus cosine of 2x over 2. And then the secant tangent situation where you can't do it is when you have secant to an odd power and tangent to an even power. So if you have like either secant of x times tangent squared x, or if you have the integral of secant cubed x dx, both of these you can't do a u sub for either. These are both integration by parts first, and then trig identity second. 1 plus tangent squared x, secant squared x. And then you end up getting the same integral you started with, and then you bring it over, divide by 2, that whole kind of craziness. Yeah. Okay. So let's change gears. I know someone asked for a physics problem. Do a physics problem, and then we could do.
Wait,
Go ahead.
for the tan squared x, did you turn it into a secant squared x?
Well, so for this one here.
Yeah.
So the idea, we actually did this problem last time. I'm happy to show you again, but let me actually let me show you secant cubed instead, just because it's different. They're really the same problem.
Oh, but James, also those two right there, they're separate problems that you wrote.
Right, they're two different.
Oh, okay. It's because I thought they were like the first line went to the second line,
but they actually are literally almost the same question. Let me show you what I mean. So the integral of, which one do I want right there? Sure. The integral of secant cubed x is the integral of secant x times secant squared x. But the integral of secant squared x is, secant squared x is 1 plus tangent squared. So it's the integral of secant x times 1 plus tangent squared x. And that's equal to the integral of secant x plus secant x tangent squared x. So the difference between the integral of secant cubed and the integral of secant x and tangent squared x is the integral of secant x, which is maybe not that interesting, but they are kind of essentially the same. Right? We know how to find the integral of secant x. It's the natural log of the absolute value of secant x plus tangent x. And so finding these boils down to being about the same amount of work. That work being the following kind of thing. Integration by parts, then the trig identity. Then you're going to get what you started with. So here, the integration by parts is that you're going to pick one thing to be secant and one thing to be secant squared. What should I pick my u to be? Should u be secant or should u be secant squared? Well,
We want u secant.
right, because the better question really is what should I pick my dv to be? What's easier to anti-differentiate? Secant or secant squared?
Secant squared.
Right, the antiderivative of secant squared is way nicer than the antiderivative of secant. We know both of them. We know the antiderivative of secant squared is tangent. We know the antiderivative of secant is the natural log of absolute value of secant x plus tangent x. The antiderivative of that's clearly nicer than the antiderivative of that. And our u is secant x. So then du is secant x times tangent x. And v is the antiderivative of secant squared x, which is tangent x. So then we rewrite this as secant x tangent x minus the integral of tangent x times secant x tangent x dx. What I've really got is secant times tangent squared. But tangent squared x equals secant squared x minus 1. So I'm going to replace tangent squared x with secant squared x minus 1. So this is equal to secant x tangent x minus the integral of secant x times tangent squared, which is secant squared x minus 1. And now comes the part where we're going to break this apart. And actually, let me write this. I'm going to write the integral of secant cubed x is equal to secant x tangent x. Now check this out. I'm going to get minus the integral of secant cubed x. And then I also have a minus the integral of secant x times minus 1, which will be plus the integral of secant x. Okay, but now look, this is just that again. So add that over there, and then you're going to get that 2 times the integral of secant cubed x is equal to secant x tangent x plus the integral of secant x, which is the natural log of the absolute value of secant x plus tangent x. And then if you divide both sides by 2, the integral of secant of cubed of x is equal to 1/2 secant x tangent x. It's natural log of the absolute value of secant x plus tangent x plus c. Fun times. So most powers of secant and tangent or sine and cosine lend themselves to being done by a u substitution. The two exceptions are for sine and cosine, if both sine and cosine are to even powers, or if you just have like cosine to the 4th, everything's to an even power, or sine to the 4th, right? You have the cosine to the 0, they're all even powers. The situation for secant tangent that does not work for u sub is when you have secant to an odd power and tangent to an even power. So here we have secant to the 3rd and tangent to the 0, or on the other one I erased, we had secant to the 1st and tangent squared. Those are when you have to do other terrible things. I should mention integrals like sine squared and cosine squared definitely do come up with, like secant cubed is kind of an oddity. You're like, okay, here's this neat problem. It's kind of fun, but whatever. sine squared and cosine squared definitely do come back up later on when we talk about when do they come up somewhere. Maybe it's more in the polar coordinate stuff that I'm thinking of. They definitely come back somewhere. Okay, let's see. I feel like it might be worth our time to start moving. Yeah, let's go ahead and move forward past trig integrals to trig substitution. So trig substitution, there is some trigonometry involved, but it's kind of funky. So I would like to find, yeah, I'm gonna start with that. Let's say I want to find the integral from 0 to 2 of the square root of 4 minus x squared. Well, first I'm going to point out we can actually do this without integration. This is a known shape. It's the top half, it's a semicircle, right? Y equal to the square root of 4 minus x squared. Looks like this. As intercept at -2 and 2. If we're going from 0 to 2, I'm just getting this quarter of a circle. And I know the area of a quarter of a circle. It's 1/4 pi times the radius squared. So the integral here should just end up equaling pi, which it does. But now let me show you another way to do it. So another way to do this is using a method called trig substitution. And the whole idea is that you want to make this thing inside the square root look like a trig identity. I want this to look like something minus something squared. So the thing is, we have kind of 3 trig identities that we're going to use. And I'm going to write them on the other side. We'll come back to this in a second. So here are my 3 trig identities. Really, it's only 2 trig identities, but we are messing with them. So the first trig identity is sine squared theta plus cosine squared theta equals 1. But we're going to rewrite it as cosine squared theta equals 1 minus sine squared theta. So the idea is we're looking to make a choice so that we have 1 minus something, 1 minus sine squared. And we also have 1 plus tangent squared theta equal to 1. Sorry, equal to what? Equal to secant squared theta. And then we also have secant squared theta minus 1 equal to tangent squared theta. So the name of the game here is to look at what you have usually inside of a square root and try and make it look like 1 minus sine squared, or secant squared minus 1, or 1 plus tangent squared. So basically, do you have a number minus x squared? Great, you try and make it look like this. Do you have a number plus x squared? Great, you try and make it look like this. Do you have x squared minus a number? Or you try and make it look like this. So of those 3, we have a number minus x squared. So I'm going to try and make it look like that. Now, the problem here is that I can't pick x equal to sine of theta. Because if I did, then I would have 4 minus sine squared theta. And that's not a trig identity. Instead, I have to make the choice to let x equal 2 times sine of theta. Watch. If I plug that in here, 4 minus x squared becomes 4 minus 2 sine theta quantity squared. Multiply that out, you get 4 minus 4 sine squared theta. Factor out of 4. And then 1 minus sine squared theta is equal to cosine squared theta. So I want to be extra clear about this. We're making the choice, we're letting x equal something. So it's kind of different than a u sub, right? You're not picking u equal to 4 minus x squared. You're actually setting x equal to something else, and you're going to plug in for that x instead of trying to capture all the stuff with u. So that's our trig substitution. And then we're going to plug in, right, we're going to change everything from x's to thetas. So x is going to be 2 sine theta. And my dx, I have to take the derivative here. So dx is equal to 2 times the derivative of sine theta is cosine theta d theta. I cannot stress enough. When you're doing a trig sub, you absolutely have to use a different variable for what you're calling your angle. You almost always want to use theta, but it's really going to cause you serious problems if you let x equal 2 sine of x. It's not going to work. The reason why specifically is because you have to make sure that dx gets replaced with what it's equal to, which is not just d theta, it's 2 times cosine theta times d theta. So this is what we get. We get the integral. The square root of 4 minus x squared is going to be, well, 4 minus x squared is equal to 4 cosine squared. So it's going to be the square root of 4 cosine squared theta times my dx, which is 2 cosine theta. And I think we might as well change our limits of integration. This is also where things get a little bit weird. Never enough room. Let me just write a few more steps and then we'll change limits. So square root of 4 cosine squared is 2 cosine theta. So you get the integral of 2 cosine theta times another 2 cosine theta d theta. And then I'm going to factor out the 4 and left with a cosine squared. So here's an example. So in these trig substitution problems, cosine squared and sine squared do come up quite frequently. Maybe that's what I was thinking of. So then this is going to be 4 times the integral of 1 plus cosine of 2 theta divided by 2. I'm going to cancel a 2 here and a 2 here. So then, I guess I can erase here. I don't really want, so yeah, let me erase this. So then, if I want to find my new limits of integration, so I have x equal to 0, which means 2 sine of theta equals 0. Sine of theta equals 0. Sine of what angle equals 0? Oh, the angle is 0. And then if x equals 2, we have 2 sine of theta equal to 2. Sine of theta equal to 1. What angle is sine of theta equal to 1 at? Anybody? Anybody? Sine of something equals 1.
Sine of 0.
Sine of 0 is 0. Cosine of 0 is 1.
Oh yeah. Would it be pi over 2?
Awesome. So those are my new limits of integration from 0 to pi over 2. So now I'm going to erase this up here since this isn't part of it. We're going to get that this integral is going to be 2 times integral from 0 to pi over 2 of 1 plus cosine of 2 theta. Integrate. Antiderivative of 1 is theta. Antiderivative of cosine 2 theta is sine 2 theta over 2 from 0 to pi over 2. And then plugging in pi over 2, we get pi over 2 plus sine of pi is 0. Minus 0 plus sine of 0 is also 0. So we get 2 times pi over 2, which is, hey, pi, just like we said it was. So this is an example of a trig substitution, where you're letting x equal a trigonometric function so that you end up getting a trig identity showing up inside your square root to make your square root simplify. That's kind of the whole gist of the idea. Let's look at another example.
James?
Yeah.
So, plus cosine. How did our Oh, never mind. I got it.
So let's look at an indefinite integral. The indefinite ones actually often are kind of harder, and you'll see why. So let's say I want to find the integral of what have we got here? That's fine. Yeah. Of 1 over x times the square root of 1 minus x squared. Okay, again, this is going to be a sign trig substitution because I have 1 minus something squared. So I'm going to let x equal sine of theta. And then I'm going to notice that 1 minus x squared is 1 minus sine squared, which is cosine squared. And then what's my dx going to be? Well, dx is going to be the derivative of sine is cosine. So now I'm going to start replacing everything. I get 1 over sine. I think it's worth writing it in here, even though we know it's supposed to equal. So I get times the square root of 1 minus sine squared theta. And then I've got dx, which is cosine theta d theta. Okay, but the square root of 1 minus sine squared is the square root of cosine squared, which is just cosine. We don't, when there's no limits of integration, we really don't worry about the square root of a square being positive or negative, which it works. So we end up getting the integral of 1 over sine cosine times cosine. We can cancel the cosine there, cosine there. So we're really integrating 1 over sine, also known as cosecant. And we know the integral of cosecant theta. There's actually two equivalent versions of it. I typically prefer the negative version. So I like to write it as the negative natural log of the absolute value of cosecant theta plus cotangent theta. But it is equally correct to write it as the positive natural log of cosecant theta minus cotangent theta. They are the same. If you really want, I can show you why they're the same, but we don't need to if you guys don't want me to. So either way is fine. Positive natural log of cosecant minus cotangent or negative natural log of cosecant plus cotangent. Now here's the plus. We're not done though, because it was an indefinite integral. We should end with the same variable we started with. We started with x's. We can't end with thetas. Now, some people, not me, would be like, well, James, we're just going to do this. We're going to say, well, let's see. Take the inverse sine of both sides so that theta is equal to the inverse sine of x, and then plug that in and write cosecant of inverse sine of x minus cotangent of inverse sine of x. It's not that it's incorrect. It's just not as correct as it should be. So there's a process here. And the process consists of drawing a triangle. What I mean is, we have sine of theta equal to x, or I'm going to write sine of theta equal to x over 1. I'm going to draw a right triangle where, well, sine is which side over which side? Oh, it's opposite over hypotenuse. So that's my angle theta. Then the opposite side should be x, and the hypotenuse side should be 1. I can find the third side now. Here's a trick or a tip. The third side is always the square root that's already in your integral, meaning it's the square root of 1 minus x squared. You can do the work, right? You can call this like a, and then say a squared plus x squared equals 1 squared. A squared equals 1 minus x squared. A is the square root of 1 minus x squared. Oh yeah, look, it's exactly that. So the nice thing about this triangle method is once you figured out the two sides you know, the third side you don't know is what square root was in your integral that made you do the trig sub in the first place. Always true for trig substitutions. So that third side is going to be the square root of 1 minus x squared. Great. Now I can find cosecant and cotangent. Cosecant is the reciprocal of sine. Sine was x over 1, so cosecant is 1 over x. Cotangent is the reciprocal of tangent. Tangent's opposite over adjacent, so cotangent is adjacent over opposite. So it's going to be the adjacent over the opposite, which is, sorry, minus. The adjacent side is the square root of 1 minus x squared. The opposite side is x. And then someone might write this as, someone would probably rewrite this as the natural log of the absolute value of 1 minus the square root of 1 minus x squared all over x. So that's a trig substitution. Or another trig substitution. Yeah, let's do some more. Let's see. I want to do one where you get. I would like that to happen. Okay. Sure. So let's see here. Sure, that's going to be similar. Right. Let's try this one. Let's do the integral. Let's do this one. It's always kind of funky coming up with problems. I just want to make sure this one doesn't come out to be super extra terrible. Let's try this one. Let's do x squared over the square root of x squared plus 9. Okay. So when I see a plus, I know it's going to be a tangent, because a plus looks like a t and tangent starts with t. So I'm going to let x equal 3 tangent theta. Why 3? Because I need that 9 needs to get taken care of by squaring 3. So really, when we're doing a trig sub, right, if you have a number here that's not 1, you're going to also throw in a factor that's the square root of that number. So that then x squared is equal to 9 tangent squared theta, and x squared plus 9 is 9 tangent squared theta plus 9. You can factor out the 9. And then 1 plus tangent squared theta is secant squared theta. Not d theta yet. Okay, great. So here's what we've got so far. We've got, let's actually start plugging something. We've got, okay, so let's start plugging things in. So the square root of x squared plus 9 is going to be the square root of 9 secant squared theta. X squared is going to be 3 tangent, well, it's going to be 9 tangent squared, right? And dx is going to be, oh, I need to find dx. So dx is the derivative of x, which is 3 secant squared theta. Okay, this is going to end up being, let's see, I've got the integral of 9 tangent squared times 3 secant squared over 3 secant, and then I can cancel a secant here and a secant here and a 3 here. So I'm left with the integral of, oh man, 9 tangent squared theta times secant of theta d theta, which is a bummer because this is one of those ones where you have to do integration by parts and then use the trig identity. So that feels lame. So I'm going to change the problem just so it's not custom. So I'm going to make a real easy change. It's not going to be a super big deal. Instead of being x squared, I'm going to make it x cubed. Yeah, x cubed. Which is only going to change this part here. So instead of being 9 tangent squared, it's going to be 27 tangent cubed. And then I'm going to have a 27 tangent cubed here. All right, this is a little more manageable. So now we can do it. So now we have to do a u sub here. So the u sub I want to do is, I want to let u equal secant or tangent. Well, if I let u equal tangent, my du is secant squared. I don't even have secant squared. So it's probably most likely that my u needs to be tangent. Sorry, secant. So u is secant theta. Du is secant theta, tangent theta. Let's go to the other side. They're right out of room for sure. So here's what we have so far. We started with the integral of x cubed over the square root of x squared plus 9 dx. We made the trig substitution that x is 3 tangent theta. And then we've got this equal to 27 tangent cubed times secant theta. Now we're going to make the choice that u is going to be secant theta. And du is going to be secant theta, tangent theta, d theta. So breaking this apart, we're going to get a secant tangent. So we're going to get the tangent squared times a secant tangent. Okay, there's my du. And tangent squared, well, 1 plus tangent squared equals secant squared. So tangent squared is equal to secant squared theta minus 1, which is u squared minus 1. So we really have the integral of 27 times the integral of u squared minus 1 du, which is going to be 27 times u cubed over 3 minus u. Let's see. Let's distribute the 27. So we've got 9u cubed minus 9u. And now we have to go back twice. So u is equal to secant. So it's going to be 9 secant cubed theta minus 27u, not 9u. Then we have to do the triangle thing again. So I know that if I solve this for tangent, tangent of theta equals x over 3. So using my right triangle, that's theta. Tangent is opposite over adjacent. What's the third side of my triangle? It's the square root of x squared plus 9. And you can either just say it's that, or you can use the Pythagorean theorem, right? You could say like this is, I don't know, let's say it's question mark. You could say 3 squared plus x squared equals question mark squared. Oh, but then just square root both sides, you need exactly the square root of x squared plus 9. So then, this is equal to 9 times secant cubed. Well, secant is not cosine, which is adjacent over hypotenuse, but the reciprocal, which is hypotenuse over adjacent. So it's going to be 9 times the square root of x squared plus 9 over 3 cubed minus 27 times the square root of x squared plus 9 over 3. Let's see. Whew. Good times with trig substitutions. Let's do another one. Yeah. So let's say I have the integral of, where'd you go here? Sorry, one sec. Yeah. Let's say we have the integral of, say, x over the square root of x squared minus 4. So one could make the trig substitution x equal to 2 secant theta. One could, one should not. Why not? Although trig substitution is a valid method that will get us the right answer with a lot of work here, there's an easier way. So just like with the other methods we've seen, we use them if we're kind of forced to, right? I don't use, I guess we haven't really talked about partial fractions yet, but right, like we don't do harder things if we don't have to. I'm going to do this by doing a u substitution. I'm going to let u equal x squared minus 4, and du is going to be 2x dx. So that 1/2 du is x dx. Oh, well, this is much nicer now. That's going to be, so x dx is 1/2 du, and that's just 1 over the square root of u, which is just 1/2 the integral of u to the minus 1/2, which is 1/2 u to the 1/2 divided by 1/2. Those cancel. So you just get the square root of u plus c, which is just the square root of x squared minus 4. You would get the same or very similar answer off the constant maybe using trig substitution, but it's way, 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 way more work. So whenever I'm integrating, I'm always looking, is there a u sub I can do? Are you sure there isn't? Double check, because a u sub is generally kind of the easiest method we have at our fingertips. Trig substitution, on the other hand, much, much more work. Well, let's look at one where you actually do have to do trig sub. So let's look at, say, the integral of dx over x to the 4th times the square root of x squared minus 4. So this is a secant one, right? So if you have 1 minus x squared or something minus x squared, it's sine. So you want to get 1 minus sine squared equals cosine squared. If you have 1 plus x squared, x is tangent because 1 plus tangent squared is secant squared. But if you have x squared minus something, then your x has to be secant, or in this case, 2 times secant of theta. Because x squared is going to be 4 times secant squared of theta, and x squared minus 4 will be 4 secant squared theta minus 4. Factor out of 4, you got secant squared theta minus 1. And we know that secant squared theta minus 1 is equal to tangent squared theta. So once again, the whole point of doing a trig substitution is making a choice for x so that whatever is inside the square root here becomes some simpler trig function squared. So that then the square root of that thing squared is just nice and easy. And it wouldn't work here to make a different choice. You'd have problems. Sometimes people try to use sine here. The problem with using sine here is if you let x equal 2 sine theta, then you get 4 sine squared theta minus 4, which almost looks like a trig identity, right? If you factor out a -4, you get negative sine squared theta plus 1. And 1 minus sine squared is equal to cosine squared. So you get negative 4 times cosine squared theta. But if you plug that in there, square root of cosine squared is fine. It's cosine. Square root of negative 4 is imaginary. We don't want imaginary numbers when we're integrating. So we cannot use sine theta when it's x squared minus a thing. We use sine theta when it's a thing minus x squared. We also need dx. So x is 2 secant theta. X squared minus 4 is 4 tangent squared theta. And then dx is equal to the derivative of secant theta, sorry, 2 secant theta, which is 2 secant theta tangent theta. You guys hanging in there? I know it's a lot of like trigonometry stuff, but hopefully this is not too terrible. It's okay if you're not hanging in there. Like you can be totally attending class and be like, I'm gonna watch it later because this is just too much to focus on. I definitely get it. I definitely fell asleep in some classes when I was in college. Classes I really liked. They were just a bad time. Like this time. This is not a good time for me to stay awake in a class. I would be like, all right, I think this stuff is interesting. I had a really great teacher. Like I was taking an upper division math class, math 150A. Teacher was a great guy, made it really interesting. I liked the material. Couldn't stay awake for the life of me. I was just like, this is a bad time for me to take a class. So luckily, we're recording this. So if there's something you want to go back and watch later, the video will be posted. Like, oh, I totally fell asleep during that part. I'm going to go watch it again. So if you fell asleep today, it's totally fine. It happens sometimes to the best of us and to the worst of us. Anyway, so if you're not hanging in, don't worry about it. You're here, that's what counts. So we were doing this trig substitution, and I wrote dx twice because I wasn't paying attention. So let's replace things. Dx is equal to 2 secant theta tangent theta d theta. X to the 4th is going to be 2 secant theta to the 4th power. And then the square root of x squared minus 4 is going to be the square root of 4 tangent squared, which is going to be 2 tangent theta. So here's what I'm seeing already. I can cancel a tangent theta and a tangent theta. I can cancel a 2 secant theta and one of those 2 thetas there. So here's what I've got. I got the integral of d theta over 2 cubed times secant cubed, and then another 2. So that's, let's see, 1 over 16. Now, we're not going to have to do the integral of secant cubed because we don't have the integral of secant cubed. We have the integral of 1 over secant cubed, which is cosine cubed. And we know how to do the integral of cosine cubed. We're going to do a u substitution. We're going to let u equal to, you guessed it, sine. Right? If this seems funky to you, right, we're really going to think of this as 1 over 16 times the integral of cosine squared, which is 1 minus sine squared times cosine theta. And so there it's a little more obvious that, oh yeah, we should let u equal sine. So the du equals cosine. All right, so we're going to get, let's see here. We have 1/16 the integral of 1 minus u squared du. We end up with 1/16 times u minus u cubed over 3. And now we have to do all the back plugging in. I'm going to erase up here because I don't really need this anymore. It's going to equal it's going to equal 1/16 times u, which is sine of theta, minus u cubed over 3. So sine cubed theta over 3. So then we have to do the triangle thing. This is our triangle thing equation. X equals 2 secant theta. I'm going to solve for secant. So I'm going to write secant theta is equal to x over 2. Or really, I might actually flip both sides and say the reciprocal secant is cosine theta equals 2 over x. So in my triangle, cosine is adjacent over hypotenuse. Adjacent, hypotenuse. And the third side is the thing that was in my integral that I erased. It was the square root of x squared minus 4. But you can also do the work. And you can say, okay, that's the height, and 2 squared plus the height squared equals x squared, and the height squared is x squared minus 4, and the height is the square root of x squared minus 4. But I will guarantee that third unknown side of your triangle is always the square root that was in your integral that made you do the trig sum in the first place. Okay, so then we're going to get sine of theta, which is opposite over adjacent, opposite over hypotenuse. So the square root of x minus 4 over x. So it's going to be 1/16 times the square root of x squared minus 4 over x minus that cubed over 3. So 1/3 square root of x squared minus 4 over x 1. All right. Let's see. Let me look at one more thing. Sure. So let me show you another problem.
Wait, James?
Yes.
I was wondering if you could turn this to the whiteboard quickly. Okay, thank you, James.
Yeah. So, got 2 more problems to throw at you guys. Let's look at the integral of x cubed over the square root of, let's make it 25 minus x squared. Is that what I want? Yeah, that's what I want, right? Sorry, let me double check. Yeah, okay, so the thing about this problem is, and actually this problem is similar to one we had before, where I changed it to being x cubed on top. While you could do a trig sub here, and we did do a trig sub for the similar problem, there's actually probably an easier way. You can do a u sub with a back sub here. So although it would totally be fine to do a trig sub with x equal to 5 sine theta, trig substitution is often one of my methods of last resort. Like I would love to do something else first. I'm going to do a u sub here. U is 25 minus x squared. Du is negative 2x dx. So I have negative 1/2 du is x dx. And if I start writing this out, I'm going to break off the x. So I've got x squared times x dx over the square root of 25 minus x squared. X dx is my negative 1/2 du. 25 minus x squared is my u. And what's x squared equal to? Oh, what's x squared equal to? I can add x squared and subtract u. It's a back substitution. X squared is equal to 25 minus u. So this becomes the integral of 25 minus u times negative 1/2 du divided by the square root of u. Which we can totally integrate if we just divide each thing by the square root of u. So this is going to be negative 1/2. 25 over the square root of u is 25 times u to the negative 1/2. And u divided by the square root of u is u to the positive 1/2. then we anti-differentiate. We get -1/2 times 25 u to the 1/2 divided by 1/2 is multiplying by 2. And then u to the 3/2 dividing by 3/2 is multiplying by 2/3. And then we just plug back in that u is equal to 25 minus x squared. So we end up getting -1/2 times 50 is -25 times u to the 1/2, which is the square root of 25 minus x squared. And then -1/2 times 2/3 is -1/3. And u to the 3/2 is going to be 25 minus x squared. Most likely much easier than doing a trig substitution. I got one more for you before my red pens just run out of ink.
James,
Yeah.
For how did we go from 25 minus u to 25u to the power of -1/2 plus?
Oh, sorry, to be minus.
Yeah, that plus was like throwing me.
Sorry, that's a minus. So I made a mistake. There we go. That's better. Other questions about this?
Oh, for my part, I'm good. Thank you, James. I understand. Oh no, just for my part, I'm good. Thank you, James.
All right, let's look at almost the same problem, which is going to be totally different. I'm going to do x squared on top instead of x cubed. I do want to get through this one because this one has some interesting little pieces that pop up here. So I'm going to do integral of x squared divided by the square root of 25 minus x squared. So now we are stuck using a trig substitution. So we're going to let x equal 5 sine of theta. And then dx is going to be 5 cosine of theta. D theta. So let's start replacing stuff. X squared is going to be 25 sine squared. And in the denominator, I'm going to have 25 minus 25 sine squared. And then dx is going to be 5 cosine theta. All right. So then this simplifies, right? We can factor out of 25. In fact, let's just write it over here. 25 times 1 minus sine squared, which is what that is, just factor out the 25, is equal to 25 times cosine squared. And then the square root of that is just 5 cosine theta. So this denominator is just 5 cosine theta. So I end up with the integral of 25 sine squared theta divided by 5 cosine theta times 5 cosine theta d theta. Great. This is 25 times the integral of sine squared. If we know a trig identity for sine squared, it's 1 minus cosine of 2 theta all divided by 2. Let's anti-differentiate this. We're going to get 25 over 2 times theta minus sine of 2 theta over 2. But again, we'd like to plug back in for theta. So I'm going to use a triangle. I'm going to use the fact that sine of theta equals x over 5. There's theta. Opposite is x, hypotenuse is 5. The third side, the adjacent side, is the square root of 25 minus x squared. Now I got a couple problems here. This is where things get weird. First of all, I've got a theta. Well, I can just solve this with theta and say that theta is the inverse sine of x over 5. So if you do have just theta showing up, you do have to write it as the inverse trig function of whatever. This is going to be 25/2 times inverse sine of x over 5. But then what about sine of 2 theta? I know that sine of theta is x over 5. What the heck is sine of 2 theta? Well, there's a trig identity for that. That should be like the theme of this section. There's a trig identity for that. So sine of 2 theta, there's a double angle formula. It says sine of 2 theta is 2 sine of theta times cosine of theta. So then if I have sine of 2 theta divided by 2, I can cancel all those. So sine of 2 theta over 2 is just sine of theta times cosine of theta. So that's sine of theta times cosine of theta. Sine of theta is x over 5. Cosine theta is the square root of 25 minus x squared over 5. So it can be a little bit tricky when you have a sine of 2 theta pop up in your answer. You have to use the identity that sine of 2 theta is equal to 2 sine theta cosine theta. And then be like, oh yeah, the triangle tells me that sine of theta is whatever and cosine of theta is whatever. All right. It's been 2 hours of nonstop math. I'm sorry I forgot to do a work or a physics problem. But next week I'll make up. Yeah, of course, yeah, sure. We can definitely do some physics problems tomorrow in office hours. Yeah. All right. I'll see you all next week. See some of you tomorrow. Take it easy.
James?
Yeah.
I have one last final question. So could you explain how we go about and how we choose our x again for when we do these types of problems?
So you're always trying to make a trig identity happen. So basically, in fact, I'll revisit this on Tuesday next week for sure. But basically, the idea is if a squared minus x squared, you're going to let x equal a times sine of theta. Because if you plug that in, you get the trig identity that you want. If you have a squared plus x squared, you let x equal a times tangent of theta. And finally, if you have x squared minus a squared, you let x equal a times secant of theta. And again, it's because you're going to get a trig identity each time, right? If you plug it in here, like so for this one, right, if you plug in a sine theta for x, you get a squared minus a sine theta squared. But then if you multiply that out, that's a squared minus a squared sine squared theta. Factor out an a squared. And 1 minus sine squared is equal to cosine squared. For this one, same sort of thing. If you let x equal to a tangent theta, you get a squared plus a tangent theta squared, which is a squared plus a squared tangent squared theta, which is a squared times 1 plus tangent squared theta. But 1 plus tangent squared theta is secant squared theta. So you get a squared secant squared theta. And lastly, for this one, if you plug in a secant theta for x, you get a secant theta squared minus a squared. You get a squared secant squared theta minus a squared. You factor out the a squared, you're left with secant squared theta minus 1. And secant squared theta minus 1 is equal to tangent squared theta. So, to reiterate, you're always making the choice for x that when you plug in whatever x is equal to into the thing that's in the square root, and usually this stuff is in a square root, almost always. There are rare exceptions where it's not, but they are very rare. you're trying to make it so that when you make that choice for x and you plug that in for x, the thing you get is some nice thing that's squared. So then you can take the square root of this and get something that's simple.